This is the Project 2 Part B video by William Morrison for Lab Section 16, Team 3 for EAS 3810C, Aerospace Design of Experiments 1 at UCF. Today I'll be showing you how to simulate Inviscid flow over a horizontal circular cylinder at a motor frequency of 60 Hz. I've created a copy of my empty wind tunnel here, and we will begin by placing the cylinder in the wind tunnel. So open up geometry. With the design modeler open, we'll now put our cylinder in the center of the test section. Start by suppressing the surface body, and then go to sketching. And then we'll draw a vertical line that spans the center of the test section by making sure that this distance, this horizontal distance, is half of the total length of the test section, which is given by H27, which is 30.5. So H36 should be 30.5 over 2. I'll just input that manually. So 15.25. Right. Now we will place our cylinder, which in 2D will just look like a circle. Centered there. And then to use a blockage ratio of 10%, we convert that to a height ratio for 2D. So we want our diameter of the circle to be 10% of the height of the test section. Which is given by V31, which is 15.306. So we will have the diameter being 1.53 centimeters. Okay. With that drawn, we can delete this line. Then back to modeling, unsuppress, generate. Now as you can see, wind tunnel is generated, and in the center is a hole which will represent our 2D cylinder. So now you can go ahead and close the geometry and move on to meshing. Double click to open the mesher. Alright, we see that the cylinder was brought with the mesh, with the geometry into the mesher. So we are prepared to mesh. I went ahead and deleted the previous mesh and also the name selection so we can start completely from scratch. So mesh, we can go to method. We'll go ahead and do triangles. And because we now have an internal surface, we should insert some inflation. And then we have to select the cylinder so it knows the boundaries. Apply that. And we're going to do 5 layers. And we should also insert some sizing. So right click, insert sizing. Select our cylinder. And then go ahead and decrease this to 1 millimeter. Okay. Let's do a larger mesh. Let's do 2 centimeters just to visualize the results. Okay. You see that dominantly there are triangles, and then as the geometry gets closer to the cylinder, the triangles get smaller and eventually turn to rectangles, which is what we want to see. Primarily for viscous flow, this simulation will be Inviscid 60 Hz, but this is primarily for the viscous flow. But it also produces more accurate results near the surface of the cylinder and also on the surface. Alright, so now for actual meshing for this simulation, we will decrease the element size to 2 millimeters, so we'll decrease the size by 1/10. Okay, and generate. With meshing completed, we now see that the size of the meshes is much more refined, which will produce better results when simulated in Fluent. So to get an overall picture, you see that the meshes are very small and not visible until you zoom in, which is what we generally want to see. And as we approach the cylinder, the triangles become more rectangular. We get the statistics of our meshing. We see that we have over 340,000 meshed elements in our wind tunnel and around the cylinder. So with meshing completed, we will go ahead and define our boundaries. Since we're zoomed in, we'll go ahead and start with the cylinder. So we'll go into Edge Select, select the cylinder, press N, and we'll name this Internal. Okay, now selecting boundaries of the wind tunnel itself, the velocity inlet, press N, name it velocity inlet. And the exit of the wind tunnel will be called the pressure outlet. So that's what it's named. Now defining the walls. Press N, name it walls. Alright, so it's a good idea to check. So internal is our cylinder. I'm going to zoom in on that to make sure the whole cylinder was named. Yep, it's all red. Velocity inlet should be here. Pressure outlet is there. And the walls span the entire exterior of the wind tunnel. So with meshing completed and boundary conditions set, meshing is completed. Once back in the workbench, you want to right click on Mesh and Update so that the mesh can be sent to the solver when selected. Once the mesh has been updated, go ahead and click Solution to open Fluent. With Fluent open, we are now ready to make the specifications that we need to run. For the purpose of this video, we are going to run Inviscid flow at a fan frequency of 60 Hz, which corresponds to a test section velocity of 14.5 meters per second, which corresponds for this geometry at approximately 4.5 meter second entrance velocity. So we'll go ahead and select models. We'll turn energy off. Okay, viscous, edit. You can't see it, but I am going to select Inviscid flow. Set that by hitting OK. You'll see Inviscid pop up here. With that prepared, we are now ready to set our boundary conditions. So we're going to double click inlet. And then as stated, inlet velocity of approximately 4.5 meters per second corresponds to a 60 hertz fan motor frequency. Alright, so we will specify velocity magnitude as 4.5 meters per second. Apply and close. Before initializing and running, we want to save. Okay, with the project saved, we're going to go ahead and confirm that we have our cylinder. This is not. Yes, okay. Just want to confirm before we run the calculation. So next we're going to go to initialization. Go ahead and initialize using hybrid initialization. Okay, initialization is complete, so let's go ahead and run our calculation. And calculate. With the calculations run and completed, we can begin data analysis. Although it's not required, it's always a good idea to go ahead and check your contours to make sure velocity is high where it's supposed to be high and it's low where it's supposed to be low, especially for simulating Inviscid flow. So go ahead and generate a meant to do velocity. Go ahead and generate a velocity contour. All right. So as you see, velocity begins low in the settling chamber and then increases down the test section. And then zooming in on the cylinder, a high velocity on top as expected, and 2 stagnation points, one on the left face, one on the right face. Another worth noting is the presence of flow on the surface of the cylinder, which is characteristic of inviscid flow. Had this been viscous flow, the whole cylinder would have been surrounded by a blue ring due to the no-slip condition, bringing velocity on the surface down to 0. Confirmed results. We can go ahead and plot. We can now plot the coefficient of pressure against the surface of the cylinder as well as the velocity of the airflow on the surface of the cylinder. In order to do this, we're going to go to plots, XY plot. We will select write to file so we can export to Excel. We're going to create a plot of static pressure against the curved length of the internal cylinder. So we're going to write that file. Save it as video 1. And we will do the same for velocity. That will be saved as video 2. Okay. Since the plots of coefficient of pressure and velocity against the surface of the cylinder are all that's required for part B of this project, fluent analysis is now complete. Now that data acquisition using ANSYS Fluent is complete, it is time to generate the plots for coefficient of pressure and velocity over the entire surface of the cylinder. Here in this column I have the arc length, which was measured by Fluent, which denotes the point on the cylinder on which velocity was measured. This column indicates the measured velocity. V infinity is the velocity of airflow in the test section generated by the fan, which is rotating at a frequency of 60 Hertz, and that produces a test section velocity of this value. And R represents the radius of the circle, which will be used to calculate the angle which is generated. To calculate that angle, we take the arc length, S, divided by R, and then convert it to degrees. So let's go ahead and do that. So theta equals S over R that'll be in radians, so to convert to degrees we go ahead and divide by pi and multiply by 180 degrees. And we will convert all our arc lengths to corresponding angles. Clearly, looks like I made a unit error. That should be that to convert to meters. There we go, because this arc length is itself in meters. So clearly increments of angles were taken at approximately 7.5 degrees by Fluent. And another noteworthy characteristic of our list is that it does not complete a full 360 arc around the surface of the cylinder. That is because if it did so, it would be measuring the same point twice, since the angle of 0 degrees and an angle of 360 degrees correspond to the same point, which is the leftmost face of the cylinder. So we have to add that point. Okay. So now that we have corresponding angles, we can simply translate our velocities over, and then to accommodate for what I explained just now, we simply add this velocity value to the end. Okay. So to generate coefficient of pressure, what we will do is utilize the fact that we simulated inviscid flow to simplify the equation for coefficient of pressure to equal 1 minus measured velocity divided by test section velocity whole square. Go ahead and calculate coefficient of pressure for all points on the surface. And then simply bring our theta values over so we can easily plot. Paste the values. Okay. We're now prepared to plot coefficient of pressure over the surface of the cylinder. So that we will generate a curved surface chart. Okay. So this is the distribution of coefficient of pressure over the cylinder of the surface. A few improvements could be made, such as this plateau being removed and simply coming down. But a good characteristic of it is it starts very near to 1. Another characteristic which could be improved is it is supposed to drop down to -3, when in fact it has a minimum value of approximately 2.3 or 2.4. As expected, it does climb back up to approximately 1. Looks like it goes to exactly 1. And then it climbs back down to that corresponding minimum value before climbing back up and reaching a value of 1. Noting distances on the horizontal axis is also noteworthy because it appears that a minimum occurs around the 90 degrees mark, which makes sense because this is where velocity is maximum. And another minimum, or another maximum, I should say, occurs at approximately the 180 degree mark, which corresponds to a stagnation point where coefficient of pressure would be maximum. And then same occurs at 270 degrees. And looks like it maximizes at about 310 degrees when in fact it should maximize at 360. So there are some errors which are likely caused by numerical errors, meshing refinement errors, possibly rounding errors. So there's plenty of things to explain, but generally it looks acceptable because it has that general squared sinusoid. Okay, so coefficient of pressure is successfully plotted. Now we simply will plot velocity over the surface of the cylinder. So to do that, move this chart over, select all these values, and perform the same chart generation. Okay. This chart also looks good compared to what would be expected. What would be expected is a start at 0 and a climb to a maximum value of twice the test section velocity at an angle of approximately 90 degrees. Instead, what we get is some initial velocity, which should be a stagnation point. It does climb up to a value that is maximum at approximately 90 degrees, but it's a little bit lower than what would be expected. It would be expected to be twice this value, so approximately 29 meters per second, when in fact it goes to probably about 26 to 27. After reaching its maximum value, velocity decreases significantly as it traverses the surface of the cylinder, reaching a minimum value at approximately the 180 degree mark. Looks like it happens a little before that, but theoretically it should happen at the 180 degree mark, since this is also a stagnation point. The curve repeats itself as it traverses the bottom of the cylinder, reaching a maximum value, which corresponds to the first one, at approximately 270 degrees. This corresponds to the bottom of the cylinder, where velocity is also maximized. After reaching the bottom of the cylinder, it moves back toward the left stagnation point, where velocity decreases, and then eventually goes near zero at approximately 360 degrees. The same errors occur due to similar reasons, because of mesh refinement errors, possibly numerical errors, or rounding errors made by Fluent. This concludes Part B of Project 2 for EAS 3810C, Design of Aerospace Experiments at UCF.